Okay, so this is Mechanics Year 13, and this is question 8, June 2017, and I'm doing this question because someone requested that I do it. Here we've got two particles, mass of 2m, mass of m, and so I've written in the weight here, which is 2mg, weight here, mg, put the tensions in here, here, and here. And so you've got this region here for the pulley, okay, and you've got this region here for A. You can see I've put in the reaction force and I've got the motion equations. So in the first part of the question, they want the motion equations for A and B. So A is moving from left to right, and it's T, okay, so just looking at A, T, take away friction, net forces equals mass times acceleration. And I've added, in the mark scheme, you've got a mark just for going T minus F equals 2ma. But because I'm going to need it later, I've put in mu is equal to, so mu they've told us is less than a half. And so we have to leave mu as just mu. So I've got the reaction force, mu r, here. But again, for the first part, you only need to get that for the mark. And here we've got the motion equation for this B is just mg take away t. So we've got this region here for B. Mg take away t equals mass times acceleration. Net forces equals mass times acceleration. So they're the marks for that bit. Now in part B, they want us to work out what the acceleration is. And if you remember, when you get these two motion equations, you can see that when you add these two equations here, so I just move my hand there, if I add these two equations here, the t's will disappear because you've got a positive t here and a negative t here. And that'll allow me to create an expression for A. So that's what I do. So I've labeled this equation 1, I've labeled this equation 2, and here you can see that I am working it out here. So I've done the t's cancelling, mg take away mu, and that was the reaction force, and you've got 2ma here and ma here, that gives you 3ma. Well, you can see I've got an m in each expression, so they all go away, and so I'm left with g minus 2 mu g equals 3a. And I factorize out the g and divide by the 3, and I get my expression for the acceleration. In part 3, they want us to work out what the velocity is of B, okay, when it hits the ground. And they want us to get it in terms of G, H, and mu. So what I'm going to do is I'm going to write out my, first of all, can I just say that things were released from rest, so that when I do my SUVAT, I know that the initial velocity is 0, and it's the final velocity I'm trying to figure out. So what I've done here is I've written SUVAT, and because they want it in terms of H, okay, I'm pretending that I know what H is, okay, because it's going to be in terms of H, so I'm going to say, okay, I know what H is, it's H. So I've left that as H. The initial, this thing was released from rest, so I've put that at 0. The V, the final velocity, is what I'm trying to work out. And I've put a little tick here to indicate that I know acceleration. Well, how do I know it? Well, I know it in terms of G and mu. So this means that the only thing, the equation I'm going to use is the last one, which if you remember is V squared equals U squared plus 2AS. Well, V squared, that's what I'm trying to work out. And U squared is easy, that's 0 squared. And so I've got 2, and A is the answer to the previous question. And remember H, they want it in terms of H, so I've left H just as H. And what I've done then is just combine the 2 and the third to make it 2/3 GH. And I brought the H to the front just to make it a little bit neater. And I've put in square root. So you can see you've got the square root symbol, and that's my answer to part C. Now in part D, they want us to work out what the distance. They say that when this hits the ground, okay, that A carries on moving. Now in the question it said that h was smaller than this distance d. So there's two parts of the journey. There's the part of the journey here which will be a distance h, which is how far it moves, okay, while it's being pulled. And then at one point when this hits the ground, it's no longer being pulled and it's just being slowed down by friction. They tell us that the thing stops just in front of the pulley. Okay, so this distance d is made up of two parts. The first part is just h, okay? Then the second part is how much further it goes when it's no longer being pulled. So what I've done here is this bit here. And you can see that I'm no longer being pulled because the other ball's resting on the ground. So there's the rope is slack. So the only thing slowing it down is friction. So I've done a motion equation. I've done net forces, which in this case is still moving in that direction. Okay, A is still moving in this direction. So that's why I've put this as a negative force. So we've got mu r, wait for the, so I had to break off there because there was two police cars going past. So what we've got here then is there's no pull. This is dragging you back, so it's negative, it's trying to slow you down. And that's mu r, okay? They tell us that mu is equal to a third. And here we've got the reaction force, and we've got the mass times acceleration. And when we work that out, I calculate that A is equal to minus a third g, okay? So here we've got the initial velocity, which was our answer to the previous question, okay, to part C. Accepting the fact that I now know that in part D mu is a third, which I'll work out later. So there's the final velocity of B was the beginning velocity of A as it was about to go under the no pull situation. We know that it comes to rest, okay, and we know the acceleration from this is minus a third g. We want to know what this distance is, so again I'm going to use the equation v squared equals u squared plus 2as. Now u, because we know that mu is a third, okay, I've got this which gives me 1 take away 2/3 is a third, and a third with that gives me 2/9 gh. And here I get minus 2/3 gs. Remember, s is what we're trying to work out. So to make this positive, I'm going to move that over to the positive side and then divide through by 2/3 g. Okay, if I do that, I get s is equal to a third h. The g is cancelling. Now you can see down the bottom here that we had two parts of the journey. So we had the bit when it was being pulled, okay, whilst being pulled as B fell to the ground. Then after B hit the ground, okay, it travels a little bit further, which we've just calculated here as a third h. So my final answer for D is 1 1/3 or 4/3 h. So I'll just quickly go over that again. So I had to recalculate the acceleration when there's no pull and only friction is slowing it down. And this gives me F equals mu r. Mu is a third. It's negative because you're going forwards and it's trying to slow you down. The reaction force is equal to the weight, and you've got mass times acceleration, giving you A is equal to minus a third g. In my SUVAT, I've got minus a third g here. Here I've got mu, okay, u rather, as the initial velocity immediately after B hits the ground. It's the same velocity as B hit the ground. And here I'm going to get a third, okay, because it tells me mu is a third. So 1 take away 2/3 is a third, and a third of 2/3 is 2/9. So we get 2/9 gh here, 2/9 gh. So I'm using u squared. Notice that I haven't got rid of the square root sign because it's u squared. Okay, so I've got u squared plus 2as, and the acceleration is 2as. Rearrange it, I get s equals a third, and I added the original h that you had here. In the last part of the question E, you might remember that we calculated that the acceleration, once we added those two equations together, the acceleration of B and A, because the string is inextensible, they have the same acceleration, and it's given by this expression here. And you can see that if mu equals a half, I get 1 minus 1 at the top here, and so I get acceleration equals 0. And that means it's only 1 mark, so it means that A and B do not move if mu equals a half, because the acceleration is 0.